Hi everyone. I know it's the last session for today, so it'll be pretty quick. Today's session is orchestrating machine learning on edge with the help of PyTorch and WebAssembly. I'm Shivay with meilisearch, and with me is Rishit from University of Toronto. So of course, we'll be starting off with what is WebAssembly. So WebAssembly is this binary instruction format that is specifically designed as a compilation target for multiple languages, whether you're talking about scripting languages or even object-oriented programming languages that can be compiled into this binary executable that can run as a platform agnostic where. So basically you can run the same WebAssembly binary on any platform. It doesn't care whether you're running it on web or you're working on a host of different types of edge architectures. It can run everywhere because it does not have to interface with the actual system architecture. It just does not care which particular CPU or host OS you're actually running it on. Now, of course, WebAssembly itself cannot do anything on its own, so it cannot directly interact with the file sources or your networking resources. For that, we basically use WASI, which is the WebAssembly system interface. So taking inspiration from how kernel kind of acts as an interface between your applications and the system itself for making syscalls. Similarly, WASI makes the syscalls for your WebAssembly modules to be able to interact with file resources or networking resources. And of course, we know that edge itself is fairly complicated, right? Because of two main reasons. First, it's a resource constraint. So in comparison to your similar systems, it's let's say 1 to 10% of the compute as compared to your standard competition. And of course, we have to deal with a number of different type of architectures, x64, 86, RISC-V, to name a few, which of course are pretty diverse in terms of their architecture. So if you are having a use case where you want to deploy a machine learning model across a host of different type of device architectures, you might have to make certain adjustments or optimizations to be able to run that model on such huge number of devices. So that's where WebAssembly is really popular choice, or a really great choice for being able to deploy workloads on edge with the help of WebAssembly. And there are primarily three main reasons why you should consider WebAssembly as the choice. First, as we kind of covered, it's highly portable, so it runs out of the box without having to make any specific integration or changes to be able to deploy it on a host of different types of devices. And in comparison to the standard way in which you will run your Python code or any other code, for that matter, on an embedded device with the help of containers. So in comparison to containers, the size of WebAssembly is pretty small, and the startup time to actually invoke any WebAssembly function or for the module is a lot smaller. So you are getting faster speeds in terms of the invocation and a much smaller size. So it makes it a very compelling choice to be able to run your workloads, and specifically since we are at a machine learning conference, machine learning workloads across a host of different type of devices. So that's why WebAssembly is a fairly good choice. And now we'll focus on Akri. So taking inspiration from Kubernetes, which is this orchestration platform that allows you to run different type of workloads very easily, and you can manage them. When it comes to like running Kubernetes on edge, most of these small embedded devices do not have compute to be able to run Kubernetes natively. So that is why we have this open source project called Akri, which essentially allows you to detect different type of leaf nodes, and these could be just different type of heterogeneous systems. It could be like cameras or sensors, and it allows you to kind of detect these different type of devices within a Kubernetes cluster, and then they kind of act as Kubernetes resources, and you can very easily just then run workloads on top of these devices. So the idea is that you could very easily just detect a lot of different type of these leaf devices within a Kubernetes cluster, and then by detecting them and treating them as Kubernetes resources, you'll be able to run your machine learning workloads on these. And here's a quick look at the Project Akri architecture. So, of course, we'll start with our leaf devices. These could be a plethora of different type of heterogeneous devices, cameras, sensors. And of course, if you're aware of the standard Kubernetes, architecture, so we have the standard Kubernetes control plane, and within this we have primarily three major things that are specific to Project Akri. So you have the Akri controller, Akri agent, and the custom broker. So these all kind of together work in sync to be able to detect leaf nodes. For example, the custom broker has this discovery handler that is working throughout the time to detect new type of edge devices. And if it is able to detect an edge device, then the Akri agent will make this particular device as a custom resource for your Kubernetes cluster, and you'll be able to very easily deploy your actual workload on this particular device. And so on and so forth, you'll continuously find more and more edge devices throughout your entire system. So over to Rishit to continue.
Yeah, so until now we talked a bit about maybe we want some way to integrate like all of these Kubernetes capabilities within edge devices to get all the benefits of auto-scaling, orchestration, and we also talked about why Wasm is a nice choice for edge deployments. So we want to talk about this a bit in the context of ML workflows and PyTorch models. So it is really helpful to somehow integrate these. How do you do that? We'll talk a bit about that. But we would be able to use the software benefits we have with Wasm. So things like the sandbox, having a thin sandbox without doing containerization, and being portable. So it's not native. You have the Wasm runtime layer, which makes it not native, but we'll soon see that it's actually pretty close to native. And since you have this Wasm runtime layer in between, your modules or components or each of the individual component instances also becomes really lightweight. So we most certainly want a way to have these advances within our deployments as well. So over here, we'll talk about one of the examples. We have a GitHub repository with quite a few code examples where we do models like NERF, which require fine-tuning or training while inference, and also standard models where we can just do inference. And we also have some other examples. But right now, let's take a look at this kind of example. I want to do novel view synthesis on my edge device, and I'll try to implement mobile nerfs, which is really popular, and deploy that on my edge device. The setting we have is there are possibly multiple edge devices, and I want some way to do scaling over those edge devices. I want some way to do orchestration, not just run them, do all the other software aspects as well. So this is until now what looks like our cluster. We have the Kubernetes control plane, which has all the standard things. We have some sensor or the edge device represented by a camera here. What our user node has is this Akri agent controller and the Akri discovery handler. The Akri discovery handler allows you to think of this as a Kubernetes resource. So now I can just think of this as I would a Kubernetes node and just use all the benefits of the Kubernetes right out of the box. And what I also introduce is this Wasm broker that allows me to schedule any Wasm workloads using this shim layer, because you don't want to use containers to do this. So on a high level, this is what it ends up looking like. And we run this Wasm, we schedule this Wasm workload to run using the API server and commands to the control plane. So in this case, what we'll do is take a look at an example where I'll try to run nerfs and manage, more importantly, manage nerfs in this fashion. So what I'll do is I'll assume we have all the mobile nerf code compiled, all the rendering and that part compiled. And what we'll try and do is think about how we would mainly write these aspects. So, but first off, what I want you to understand is we have like this Wasm module or Wasm component that's being created from inference code in any language, and until now it's all portable, but because we have like this Wasm runtime layer in between. But you could most certainly have something like AOT artifacts and still get all the benefit of native and AOT from a Wasm module. Which would, of course, mean it sacrifices portability. So actually, let's take an example of what happens, or I'll at least show a bit of it, how much I'm able to show in this short talk. We have a code repository where we not just do mobile nerf, but also instant NGP and other models. Mainly what I want to show you is I have some Akri agents already deployed. I also have my Akri controller, and I have these Akri agents, just like we talked about in the architecture. Now, what happens is I deploy all of these on some control plane cluster, and what my discovery handler looks like is in this case, I just implement the discovery handler in Rust and then compile that down to WebAssembly to show that it's truly interoperable. The IR is truly interoperable. So especially what I do in this discovery handler is I try to get this device and then through some protocol, and then simply I can simply start using all the Kubernetes functions to do this. And Wasm, though not native, performs pretty well for mobile nerves and almost real time for these rendering results. So that was a short demo. Feel free to check out our code repository. This was a very short talk, so couldn't walk through the whole thing. But that was about the talk. Thank you.
Thank you.
I have a question. So the PyTorch operators themselves, are those compiled also to WebAssembly, or are those linked in as an external?
Yes. So the question was, are the PyTorch operators themselves compiled to WebAssembly, or do you link them somewhere? So there's ability to do module linking with WASI and WASI-NN, which we don't really talk about in this talk, just for brevity. But what you would do is within each of these component instances, you also have something. You have a module linker for WebAssembly, and what that allows you to do is just run any of these other native or any of these other system binaries and use that kind of support for WebAssembly as well.